Once again, let's imagine we have a river, and we have a vector field that describes the flow rate of this river. At the beginning, the flow rate will be nice and smooth, so the vectors will all be the same length and going in the same direction. But maybe up ahead there are some rapids, so in one spot there's a long vector representing water going quickly, whereas right next to it the water's going slower, so we have a shorter vector. And then farther up ahead we have a little eddy current where the water spins around, so we have the vector spinning around in a circle. Now let's pretend that we put a ball in each of these three locations. We'll put the ball just underneath the surface, and we'll pretend we can fix the location so that the balls don't float downstream. Now we ask the question, will the current cause these balls to spin? Well, around this top ball, the current is clearly spinning counterclockwise, so the ball would also start spinning counterclockwise, and it would spin around an axis perpendicular to the surface of the river. Around this middle ball, the left side is definitely pushing faster than the right side, so that would cause the ball to start rotating clockwise, again around an axis perpendicular to the surface of the river. Around the bottom ball, the current is nice and even. You can see that there's nothing that would cause this ball to start spinning. Now that we're getting good at this, let's go deeper underneath the surface of the river. We'll say that at one depth, the water is going quickly, but then slightly lower, the water is going slower. If we place another imaginary ball here, we can see that the top of the ball would get pushed by the quicker water, and so it would start spinning like this. This ball's spin axis would be parallel to the surface of the water. What we've been doing here is finding the curl of this river's vector field. Curl answers the question of how will the ball spin at any given point in the vector field. If the vector field would make a ball spin very quickly at a certain point, then the curl at that point will be very big. If the vectors wouldn't cause a spin at all at that point, then at that point the curl will be 0. But you need more than just a number to describe curl, because there are different directions in which the ball could spin, so curl has to be a vector. The curl vector points along the axis of the ball's spin, but it could point up or down. So we use the right-hand rule to decide which direction the curl vector should point. Take a look at the top ball. Take your right hand and curl your fingers around the spin axis of the ball in the direction that the ball is spinning. Then give a thumbs up. That's the direction that the curl should point. Try doing the same thing with the middle ball. If you try to curl your fingers around the spin axis in the direction of the spin, you'll see that the only way to do it is by holding your hand upside down. So your thumb, when it extends, will point downward. Try the right-hand rule on the ball at the bottom of the river, and you'll see that your thumb has to point horizontally inward towards the center of the river. Let's review. These vectors would make a ball spin clockwise, and by the right-hand rule, that means that the curl should point into the screen. These vectors would make a ball spin counterclockwise, so by the right-hand rule, the curl should point out of the screen. If you have a clockwise eddy current, then the curl goes into the screen, and if you have a counterclockwise eddy current, then the curl goes out of the screen. Take a minute now and make sure that you're comfortable with this. If you need to, pause the video and use your right hand to find the direction of the curl in each of these situations. Now let's look at the math. If we have a vector field f, then the curl of f is del crossed with f. This should remind you of the divergence, which is del dotted with f. Remember that del is a vector with an x component of partial derivative with respect to x, a y component partial with respect to y, and z component partial with respect to z. We'll say that the vector field f has components p, q, and r. So the curl of this vector field will be these two vectors crossed together. Remember, to find the cross product of two vectors, you have to find the determinant of a matrix. The top row of the matrix are the three unit vectors I, j, and k. Then the middle row is the first vector that you're going to cross, so that's del. And the bottom row is the last vector that you're going to cross, so that's our vector field f. The determinant of this matrix will be the first element times this minus that. So that's I hat times partial of r with respect to y minus partial of q with respect to z. Then we subtract the second element times this minus that. So that's minus j hat times partial of r with respect to x minus partial of p with respect to z. Now we add the last element times this minus that, which is plus k times partial of q with respect to x minus partial of p with respect to y. This is the full equation for the curl of a vector field, but don't memorize it. It's too complicated, and a lot of the times most of these derivatives are zero. Instead, just remember that the curl is del crossed with f, and know how to take the cross product of two vectors using determinants. Now let's do a short example. We'll find the curl of this vector field. Take a look at it and you'll see that the vectors all look like they're spinning around clockwise. With the right-hand rule, we know that a clockwise spin gives a curl that goes into the page. Now imagine that we put a ball near the top of the graph. The vectors above it would be a little bit stronger than the vectors below it, so this would again cause a clockwise rotation in the ball, which is a curl into the page. Anywhere that you try it, the vectors cause a clockwise rotation. This leads us to conclude that the curl at every point in this graph is pointing into the page. Now let's actually calculate the curl to see if we were right. The horizontal axis is x, the vertical axis is y, and our vector field f is y I hat minus x j hat. To find the curl, we'll just construct our matrix. ijk on the top row, del in the middle row, and f on the bottom row. So that's y minus x, and since there's no z component, the z component is 0. The determinant will be I times this minus that. So that's I times partial of 0 with respect to y, which is 0, and partial of negative x with respect to z, which is also 0. Now we subtract j times this minus that, and that's j times partial of 0 with respect to x, which is 0, minus partial of y with respect to z, which is again 0. Finally, we do k times this minus that, which is k times partial of minus x with respect to x, which is minus 1, minus the partial of y with respect to y, which is also 1. So we have k times negative 1 minus 1. That gives us the curl of this vector field f is minus 2 k hat. This is exactly what we expected. We expected the curl to be in the minus z direction into the page, and that's what we see when we actually did the math.